Good morning, students. We'll start with Module 3 today. The Module 3 is what we have is the Module 3 is what is the chapter name, the Module 3 name, what we have, the flip-flops and its application. Now, here, what we study is we'll understand what you mean by basic bistable elements, right? We'll understand what you mean by latch and also a flip-flop. I'll give you an overview of the difference between latch and flip-flop, and we'll go to master slave. We'll understand the concept of master slave, like what do you mean by master, what do you mean by slave, right? With respect to a flip-flop, right? Here what we study is a pulse triggered flip-flop, SR flip-flop and JK flip-flops. And also we'll study of the characteristic equation. We'll study registers, binary ripple and synchronous counters, right? This is what the syllabus what we have for module 3, and this is a textbook. As you can see from this here, everyone can see the PPT, right? For this module 3 you need to refer this digital principles and design. Yes, no, everyone can see the PPT. I can see that it's been shared here. Okay. Okay, everyone need to refer this textbook, the Donald G, right? The digital principles and design, right? Everyone please do refer this the textbook what we have in digital principles and design. And we know about the course learning objectives, right? We can see from this one what we study here as part of this module 3, what we have is latches and flip-flops. We'll study registers and counters, right? And the course outcome what we have is at the end of this module 3, what you'll be learning is you have an understanding on latches, flip-flop, SR flip-flop, JK, D flip-flop, T flip-flops, right? You have understanding on registers and counters. First, here, if you see this one is the module 3 is nothing but flip-flops and its applications. In module 1, what we studied about combinational logic. The concept of what do you mean by combinational logic? What do you mean by combinational logic? Anyone? What do you understand by combinational logic? You mute yourself and huh? I'm not sure whether you're listening or not. Okay. We know that when I say combinational circuit or network, we know that it is nothing but what it's defined as a two valid network in which output at any instant are dependent only about the input present at that instant. It means that the output depends on the input combinations what you apply at that instant of time. Depending on the input combinations what you apply, the output will change, right? That is nothing but combination circuit or a network. And also given a definition for sequential network. What do you mean by sequential network? Again, sequential network is a two valid network in which output at any instant are dependent not only upon the input present at that instant but also upon the past history or sequence of inputs. What do you understand by this one? Sequential networks, right? As I said, in combination, it depends on only the combination of inputs. Whatever the combination of inputs you give at that time, the output will change. The output will be reflected according to the combination of inputs what you apply there, right? But when it comes to sequential network, it not only depends on the present inputs, but also it depends on the past history, right? Right. Since it depends on the past history of the inputs, right? Sequential networks are said to have memory because it is dependent on the past inputs. In order to preserve these past inputs, the sequential network is said to have memory. We'll understand how the flip-flops are acting as a memory element. We'll understand that one. Right? In the sense, as when we discussed in module 1, in briefly I gave an understanding on what is a combinational circuits and a sequential circuits. Right? It means that when I say sequential circuit, it is nothing but it consists of a combinational circuit to which memory elements are connected to form a feedback path. Since we have a feedback, it is dependent on the past history of inputs there, right? If you see broadly, the sequential circuits falls under two categories. The first one what we have is synchronous sequential circuit and asynchronous sequential network. What to understand by synchronous and asynchronous sequential network? When I say synchronous sequential network, here it means that the values of the signal are, are determined at only discrete instants of time. It means that when I say synchronous sequential network, here the values of the signals are determined at only discrete instants of time. But when it comes to asynchronous sequential network, the output, the states what we have, it immediately affected by the input signal changes there. In the sense, what I'm trying to say with respect to sequential and asynchronous in the sense, here when I say at only discrete instants of time, right? And when it comes to synchronous sequential circuit, the outputs, the output changes take place only at discrete instants of time. But when it comes to asynchronous, here the output changes take place immediately after changes in the input signals. Right. In the sense, when I say only, when I say with respect to sequential circuit at only discrete instants of time, here we use a clock signal. Whenever we apply the clock signal, right, depending on the input, the output will be changed. Depending on the clock signal, the output will change in synchronous circuits. But when it comes to asynchronous sequential circuits, here it is completely dependent on the input signals. Whenever there is change in the input signals, immediately the output states will be changed here. Right? This is a fundamental difference between a sequential circuit and an asynchronous circuit here. In the sense, if you see, when I say synchronous, we use a clock signal. When it comes to asynchronous, we don't have a clock signals. It is completely dependent on the input signals what you apply. Depending on the input signal changes, the output will also be immediately be reflected there, right? Now, here as part of this module 3, what we'll study is about flip-flops. We studied about flip-flop, master-slave, flip-flop, SR flip-flop and JK flip-flop, what we'll study. If you see, the basic logic element that provides memory in many sequential networks is a flip-flop. So we call as a flip-flop as a memory element. And if you see the core are central to any of the flip-flops circuits what we're going to study is bistable element, right? The first thing what we'll study is, in order to understand the flip-flops, first we'll study what you mean by a basic bistable element. We'll go to latch. We'll understand what you mean by latch, and we'll try to differentiate between latch and a flip-flop. After that, we'll study SR flip-flop and JK flip-flop in detail with respect to master-slave concept. Right? The first thing what we'll study is bistable elements. This is a diagram of a bistable element. As you can see from the diagram what we have, this is nothing but a cross-coupled NOT gates what you can see from this diagram here. As you can see here, the outputs of the NOT gate will act as an input to the other NOT gate. In the sense, You can see from this one, yeah. The output of this NOT gate acts as an input to this NOT gate. Similarly, what we have, the output of this NOT gate is acting as an input to this NOT gate here. This we call it as a cross-coupled NOT gates. In the sense, the output of the either of the NOT gate is acting as an input to the other NOT gate here. Now, if we see this one, what we have, as you can see from the diagram, what we have two NOT gates and we have two outputs. The output we call it as a Q, the other one is a Q bar here, right? This Q we call it as a normal output and Q bar we call it as a complement output here. Now, as you can see from this one, the output of the other NOT gate is acting as an input to the other NOT gate here, right? In the sense, if we call this as a first NOT gate and this is a second, the output of the first NOT gate is acting as an input to the second NOT gate. Similarly, the output of the second NOT gate is acting as an input to the first NOT gate, right? Everyone can understand from this diagram now, right? When I say cross-coupled NOT gates. Now you can see from this one, there is no inputs here, right? The outputs are acting as an input to the either of the NOT gates here. We'll assume that the X input what we have, the X what we have, this is the X what we have, which is nothing but which is equal to Q bar. We'll assume that the X is equal to 0. We'll assume that X is equal to 0 here, right? In the sense that we have X here, right? And now this is equal to 0. When X is 0, what you understand by this one? You know that the Q bar is also 0, which is nothing but Y bar, which is equal to what? The Y bar is also equal to where? Because here the input is Y, the output of the second NOT gate is Y bar. Similarly, the input to the first NOT gate is X, the output of that we call it as an X bar, and here it is, which is nothing but equal to Q here. We'll assume that the X is equal to 0. When I say X is 0, it means that the Q bar is 0, the Y bar is equal to 0 here. So that what is an output of the first NOT gate? This is equal to logic 1. So that what is the Q is equal to? The Q is also equal to 1 here. As we know that the output of the first NOT gate acts as an input to the second NOT gate. So that what we have? The Y is equal to 1 here. Since Y is 1, what will happen to the Y bar? This is again it is equal to 0. So that the Q bar is also equal to 0 here. It means that when we assume the X is equal to 0, right, we know that the Q is equal to 1 and Q bar is equal to logic 0 here. And B states what we have it, right? It stores the binary symbol. The storing of this binary symbols, we call it as the content. We call it as a content or the state of the element here, right? And now assume that the X is equal to 1 here. When X is equal to 1, what to understand by this one now? We know that Y bar is 1 and Q bar is also equal to 1 here. And what is an output of the first NOT gate? When X is 1, this is equal to 0. Therefore, Q is equal to 0. Now the output is connected as an input to the second NOT gate, so that Y is equal to 1. Since Y is 1, what is Y bar? Y is what here? Sorry. The Y is 0. Since Y is 0, what will be the Y bar? It is 1 and Q is 1. It means that when X is 1, the Q is 0 and Q bar is 1. It means that what I'm trying to say is that since the output will act as an input here, it means that whenever you switch on the power for this bistable element, right? This bistable element will always be there in one of the two stable states. The Q could be 0 and the Q could be 1. Both of these logical symbols what we have, which is stored into the element, both these logical states are stable states, so that we have logic 1 stored and logic 0 stored there. Right? Both the states are stable. That's the reason it's called as a bistable elements. Right? As we know, as I say here, we have Q and Q bar. As I said, either Q is nothing but the normal output, Q bar is nothing but complementary output. If Q is 0 here, the Q bar will be 1. Similarly, if Q is 1, the Q bar will be 0 because it is complementary output here. Right? Everyone understood about this bistable element what we have it here? Right? It means that whenever the power is switched on, right, it will be stored. The element will be having a value which will be storing the binary symbol logic 0 and 1, and both of these states are stable states there. Okay? This is a basic bistable element here. And whenever remove the power, what will happen? The state will be removed there. Understand? This is about the bistable element. Everyone understood this one about bistable element? We'll go to the next. Now, since now we know the understanding on bistable element, now we'll go to the next topic, which we call it as a latch. If you see latch, normally latch is nothing but what we have it. We always, when it comes to latch, we discuss about, as I said here, we discuss about the sequential circuits. Broadly, the sequential circuits are divided into, categorized into two circuits. One is called as a synchronous, the other one is called as an asynchronous circuits. When it comes to latches, latches are asynchronous in nature, but when it comes to flip-flops are synchronous in nature. In the sense, when I say latch, it means that the timing of the output changes in latches is not controlled. But when it comes to flip-flop, we can control the timing of the output changes. Right? In the sense, in flip-flops, we use the clock signals. We use the clock signals. But here in latch, we don't use the clock signals. If you see in the when I discussed about this one, synchronous sequential circuit. When I say synchronous sequential network, it means that we're using flip-flops there, right? It means that we're using a master-slave generator in order to generate the clock signals, and depending on the clock signals, the output values what we have, the output values will change there. That's what I have written it here. The values of the signals are determined at only discrete instants of time. Depending on the clock signal what you apply, at that instant of clock signal, the output changes will take place. It means that the output changes are controlled when it comes to synchronous sequential network. This sequential network, synchronous sequential network, are also called as clocked sequential network because we are using the clock signals in order to control the output changes there, right? But when it comes to asynchronous, we don't use a clock signals, and whenever we apply the input signals there, depending on the input signal change, the output will be immediately affected, so that the output is not controlled. Right? You understand here? That is the basic difference what we have with the latch and flip-flop. Guys, I will give more information as we proceed with this module 3. First, we'll understand one particular latch which we call it as a SR latch. Right? Here, if you see this one, SR latch, what we have it. If you see, we'll go back to the basic bistable element. When Q is 1, when the output, the Q, which is the normal output, is equal to 1, we call it as a one state. We call that as a one state or a set state, right? And when q is equal to 0, we call it as a zero state, or we call it as a reset. And when I say yes or latch, yes stands for reset, R stand for reset here, right? And again, if you see for this, again this is the output what we have it q and q bar here. This is a normal output, and the q bar is our complementary output what we have. And you can see that there is a feedback from output to the input to the other NOR gate what we have it here. So that this is also a sequential circuit, right? Now here if you see in this one what we have two NOR gates, right? To the first NOR gate what we have, the one of the input what we have, we call it as, we labeled it as R. For other NOR gate, the one of the inputs we have labeled it as yes. This yes stands for set, R stand for reset here, right? And the other input to the NOR gate is nothing but which are the inputs which we receive from the other NOR gate output here, right? I can see from this one, right? This output is connected as the input, one of the inputs to the NOR gate. Similarly, the output of this, the second NOR gate, is connected as an input to the one of the inputs to the first NOR gate here. First, we will understand how this works, right? And you can see here, this the NOR gate circuit is equivalent to what we have it, this one, an OR followed by a NOT gate, right? And the behavior of this SR latch is given by the function table what we have. In the sense, what it says is that if you can see from the function table what we have it, when S is 0 and R is 0, the outputs what we have, the output is equal to Q and Q bar here. Yes, everyone should be give attention here. Here you can see here what is written here, Q plus bar here, right? What we have is here Q. What we have it here, this is Q and this is Q bar here. And if you see, whenever you see Q plus a Q plus bar there, it means that we call it as a next state. We call that as a next state, in the sense, depending on whatever the input combination you give, right, the outputs, the Q and Q bar will change here, right? And for whatever the previous input S and R, whatever the outputs we had it there, that we call it as a previous state. We call that as a previous state, right? Yes, everyone can understand this one. If you see this, what we have it, we have Q plus, right? In some of the authors, you can see we call it as a Q T plus 1. We have T plus 1 here, right? This we call it as a next state. Next state here, right? And this Q and Q bar, what we call it as a the previous state or the present state here. We'll understand this one as I will explain what you mean by a next state and a present state. I will try to differentiate between these two as explain about the functionality or the behavior of this SR latch here. Yes, what you should understand here is when S is 0 and R is 0, right? 0, the next state is equal to nothing but the previous state itself. In the sense, I will explain this one in the sense, the next state is equal to the previous state itself, right? In the sense, if 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 previous state is 0, the next state is also 0. If the previous state is 1, the next state is also 1. That's what it says here, right? Next, what we have, when S is 0 and R is 1. When R is 1, it means that reset. What do you mean by reset? It is nothing but zero state. It means that the Q output, the next state is equal to 0 here. The output is equal to 0, right? Since the complementary output will be 1 here. What you should be really worried about is this, the normal output. Because if we know Q, we know what is the output for the Q bar, because that is nothing but the complementary of the Q. Similarly, when S is 1 and R is 0, when S is 1, what you understand by set state? We call it as a set state. It is a 1 state. The output is equal to logic 1 there, right? Similarly, when S is 1, R is 1 here, right? Here it is 0 and 0. Here we call it as an undefined state. We call it as a forbidden state. In the sense, what we have is, in the sense, since we have normal output and complementary output, the output should be always be complementary to each other. The Q and Q bar should be complementary to each other. But here, when S is 1 and R is 1, there are instances when the Q is also 0 and the Q bar is also 0, which is not defined. We call that as a forbidden state there, right? And I'll explain about this one in detail. Everyone understood about this one? At least the function table, what you understand by next state, right? The previous state. Well, just a minute, I'll go to the screen. Everyone can see this, the Microsoft whiteboard here. Everyone can see this one. I'll draw that diagram.
Yes, sir.
Okay. This is nothing but R input. This is, yes, we know that the output of the first NOR gate is Q. The second NOR gate is Q bar. The Q is our normal output. The Q bar is our complementary output. Right? We know the function table now. Right? Now here, I'll just write Q plus here. I'll write it as Q here. Right? This we call it as what? Next state. This is the next state what we have. And what is this one? Is element? The previous state. I'll call it as a previous. Previous state here. Please just bear with this writing. Yeah. Right. Now first we'll assume that the Q what we have, this is equal to logic 1. Since it is a complementary, this is equal to 0 here, right? It means that now what I apply is, now we'll take that S is equal to logic 0 and this is equal to logic 0 now, right? We'll understand this one when S is 0 and R is 0, and we'll assume that the previous state what we have, previous state, this NOR gate was storing the output, the Q was is equal to logic 1 and Q bar is logic 0 here. Since this is q is 1, what we have it here? 1 here. Hello, everyone can see this one? Hello.
Yes, sir.
Okay. Yeah. Now how this works now? Anyone? Explain me this one. Anyone can explain me this one? What is an output of the NOR gate? Anyone? Now we have a OR gate. One of the inputs is 1, the other one is 0. For OR, what we have? If one of the inputs is high, the output is high. For NOR gate, it is complement of that one. Right? So that what is an output of this NOR gate? This is equal to
Zero.
0. Right? Since it is 0, what will again, as I said here, the output of the second NOR gate will also act as an input to the first NOR gate, so that when both the inputs are 0 0, what is an output of this one? It is equal to 1 here. It means that what you understand by this one? It means that when q is 1 and q bar is 0, and the input what we have applied is s is 0 and r is 0, the next state what we have, right, means the output has to change depending on the input what we apply here, right? When s is 0 and r is 0, still the output, the next state what we have, the next state is equal to what? 1 here, right? Here for the complementary, it is still equal to 0. It means that the next state is equal to the previous state. The next state is equal to the previous state here. Everyone understood this one, right? Okay. Now we'll take that. Now this Q output is equal to 0. Since Q is 0, the Q bar will be 1. It means that now this is like a present state. Like when R is 0 and S is 0, we know that the output what is produced is 0 and 1, right? Now again, the input what we have, this is still, now S is 0 and this is equal to 0. R is also equal to 1 here. Now for this input what you applied, the whatever changes you see in the output, that will be our next state. So that when I say about the next state, it means that the whatever the output we which were produced before, that we call it as a previous state, so that this outputs will become the previous states. So that what is the previous state we have it is 0 and 1. The q bar is 1 here. Now we know that since q is 0 here, right, and this acts as an input to one of the second NOR gate what we can see here, right? So that when both are 0 0, what will happen? The next state is the q bar is equal to 1 here. So that this is nothing but what we have, q plus the next state what we have it, right? This is 1 here, right? Since this is 1, what will happen? What is an output of this? The first NOR gate, this is still equal to 0, right? So that the what we have it here, the next state what we have, the q plus what we have, this is equal to 0 here, right? And now when I apply the next input here, right, before the input, the whatever the input I apply, and I can see that changes there here. Now this becomes what? The present state. You understand the difference between the previous state, the present state, and the next state, right? So that what we have, the next state is still equal to 0 here. So that what we have, the previous state was 0, the next state is equal to 0. So similarly for the q bar, as I said here, right, it is still equal to the previous state. We understood this one, right? In the sense, what I'm trying to say is that everyone can come to this, everyone can see the PPT, the function diagram here. What I'm trying to highlight it is in the sense, when S is 0, R is 0, the next state is equal to Q, right? In the sense, if the previous state is 0 here, what you understand by the next state is also equal to 0. If the previous state is 1, the next state is also equal to 1. The same thing what I explained there. Everyone understood this one? Then when S is 0 and R is equal to 0, the next state is equal to the previous state. Whatever the state means, whatever the value which is stored in Q. If the Q is 0, the next state is also equal to 0. If Q is 1, the next state is equal to the Q plus 1 is also equal to 1 there, right? Next what we have is S is 0 and R is 1 here, I'll just clear this one. Okay, right. Now we'll assume that this is equal to 1 here. This is equal to 0. Now I'll apply R is equal to 1, S is equal to 0. Right. Now what we have, Q is 1 here. So that as we know that the Q is one of the inputs to the second NOR gate. Since it is 0 and 1, what we have it for 0 and 1, what we have it here? 0 and 1, what we have it here? It is 0, right? It is 0. So that this is 0. 1 and 0, what we get here now? 1 and 0, this is equal to what? 0, right? Now as I said here, since the output Q is acting as an input to the second, this one, when both are 0 0, what will happen here? This is equal to 1 here. It means that what I'm trying, in a sense, when R is nothing but reset, S is set. It means that when R is 1, it means that the output will be reset. The output will be in 0 state here. This is equal to 0 state here. In the sense, irrespective of whatever is the previous state, the output will always be equal to 0. If the previous state is 0, the next state is also 0. If the previous state is 1, the next state is also 0. The input is equal to what? R is equal to 1 and S is equal to 0. This state we call it as a reset state or a 0 state here. Right? Everyone understood this one? And what I will do is we'll try to show this one in the simulator. Right? Everyone can see this logic simulator here. Okay, now it's shared. Everyone can see this one now, right? Now what we have, R input and S input. This is nothing but the Q, the normal output, and this is Q bar. And now yes, R is 0 and S is 1, right? The sense will assume that both are 0 0. When both are 0 0, whatever is the previous state, the next state is also equal to same. So that what we have, this is 1 and the Q bar is 0. Now I'll make R as 1 here. Now R is 1. So that what is happening here? When R is 1 and S is 0, the Q output, what we have it? The Q output is 0 and Q bar is 1. Since the Q is 0 here, right? 0 here, we call it as a reset state or a 0 state, right? When both are 1, as I said here, when both are 1, we as I said here 0 0, right? Which we call it as a forbidden state or an undefined state, right? As we know that for this a stable element, the outputs are complementary to each other. If one output is 0, the other output should be 1, right? Both should be complementary to each other. But when we apply S is 1 and R is 1, the output is equal to 0 here, right? Which is undefined state here. And now what we have? Now S is 1, R is 0. This, so that the output, what is happening to the output here? The output is equal to 1, which we call it as a set state, or one state here, right? Irrespective, when I say yes is 1, irrespective of the previous state, the output is always equal to logic 1, right? Let everyone understood this one. We'll come to this function table. This, when R is 1, the output is always equal to 0 irrespective of the previous state. If the previous state is 0 or 1, the next state is always equal to 0 here. Similarly, if S is 1, which is S is nothing but set state, right? Irrespective of the previous state, the output, the next state is always equal to logic 1, irrespective of the previous state, because it is a state. If S is 1, R is 0, the output is always equal to 1 here. And when both are S and R are 0, 1, 1, it is forbidden state, or we call it as undefined state here. Have you understood about this? The function of an SR latch here, right? As I said here, the latch are nothing but asynchronous in nature. When I say asynchronous in the nature, whenever there is change in the input, the output change takes place.